lot for joining. And again, you brought a book.
I had. I just happen to have this here, which I'll put up for reassurance. Yeah, I totally agree with Larry. I wrote an article for Physics Today in February about how you can bring down the cost of $10 billion missions, perhaps by a factor of 2, by using mass instead of to play off against complexity. That's not what I'm going to talk about. Instead, I'm going to talk about finite concentrated resources on the moon and asteroids. Accepting this invitation, I wasn't clear what time scale of the future I should look at. I'm looking here at about 50 years maximum. I could also talk about 500 years if you'd like, and that would be quite interesting, but that's a different talk. Okay, so the key takeaway is that almost all of the moon's resources are concentrated in a fairly small number of regions, and those regions are a few kilometers across, and a few kilometers is an important size. So that's a problem, and the South Pole is a great illustration of this problem, and I'll show you about it. At the South Pole, there are regions of high illumination, which are dubiously called the peaks of eternal light, and everybody quibbles. It's not really eternal because there are 20-hour periods where it's good, it's beautiful, so let's stick with it. So not all the resources are something you can dig up and take away. In this case, the peaks themselves are the resource because of the solar power you can collect from vertical solar panels that rotate during the month. And these have nearly permanent sunlight, and they're right next to the permanently shadowed regions where most of the water is said to be, or thought to be. And so you have continuous power near a valuable resource, and that's a great way to start an industrial revolution. But it's a rare resource because the total area is a few square kilometers at most. It depends on the illumination you require and the height of the solar panels, and we've studied that.
That's distributed over several different peaks, though, right?
I think I have a map of them coming up. We've also looked at the total amount of power you can get from these, and for 20-meter high towers, you want illumination 90% of the time. That comes out to a few megawatts. So that's the maximum you can get by populating the whole surface with towers, solar power towers. That was done by Amir Ross, one of my students. No, I don't have the picture, I'm sorry. Those regions are very narrow ridges, crater rims or ridges between craters. And so they're very narrow and a few kilometers long, like 100 meters, 200 meters wide, that sort of thing. So then there are the purple areas, blue and purple areas on this map, which are the permanently shadowed regions right next to the peaks of eternal light. And when they get below minus 110 Kelvin, water ice is stable in the vacuum, and so they can retain volatiles for gigayears, and they appear to have done so. There could be as much as a billion tons of water, maybe 500 million, it's very uncertain, within factors of a few. And this is the key to lunar industry and settlement most people talk about, because you can use this for life support, and you can separate it into hydrogen and oxygen with electrolysis to make rocket fuel. And that could be an export from the moon at an early stage. It's a lot, but it's not a huge amount. It's finite. It's about 400 Olympic swimming pools. That's still quite a lot, because at a reasonable efficiency and 100 tons per export, you could export 100 units of rocket fuel. And so, did I say 1 million or 100? 1 million rockets could go off with some, so you could get some kind of industry going, but it's a finite resource and you will use it up. And so there are going to be competing uses for that scarce resource. And rocket fuel, there you go, depletes the resource, and whereas life support can be recycled at high efficiency, but not infinite efficiency, not perfect efficiency. While you're doing that mining, it's a dirty process. It creates vibrations, which can be a hazard for science instruments, telescopes, gravitational wave detectors, and the like. And so there's a conflict there in some level between the different possible uses. Because it's all got out of order. Okay. One example of other uses of the moon are putting a radio telescope on the far side. The ultimate, initially you can put it anywhere, but eventually you want one about 200 kilometers across in order to get enough resolution on the sky to resolve individual clumps of hydrogen in the dark ages before there were stars or galaxies. That means you need a large, smooth area. For rovers, typically you can't go above a 15-degree incline, which is pretty shallow. But the far side is mountainous, so we looked at 8 plausible sites with my student Zoe Leconte, and she found, looking at the LiDAR data, that 3 of them were too rough, 2 of them were too small, and only 3 good ones remained. So those are very special sites that need some kind of protection against radio interference, both nearby on the ground and from orbiting satellites that we very much want from other reasons for navigation and communication on the moon. And there are several projects already starting up to do that, to put such a constellation up. How do we protect these sites against their radio interference? It's an important question. I just want to point out that the finite concentrated resources argument applies to asteroids too. In fact, that's where I started this. And if you look at the things you might want to mine, platinum is one, for instance. They're only found in about 1% of all asteroids, near-Earth asteroids. But the ones that we know about that we can, oops, let's see if we do it. The ones we can, oh, well, never mind. That was a beautiful animation that shrank the, let me go back, shrank this bit down to about this size, because that's the fraction of all known near-Earth asteroids that we can actually get to with today's rockets. Not with Starship, that will be a bigger number. But it ends up meaning a handful of asteroids are actually reachable. And I wrote an equation to do that. Which means if you know which asteroids they are and haven't told anybody, that's intellectual property that you can sell. Okay, there valuable real estate leads to arguments. Many players are about to enter, which makes it more complicated than just 2 players. So it leads to a problem for governance. The fact that the resources are finite, though vast, is a problem for ethics. Who gets to use them? Can we use them all up and then our grandchildren can't? Or do the first comers, are they incentivized to use them up quickly and grab them before any other people come along and grab this finite resource? So there's a lot of interesting issues there. Also on a longer time scale, you can apply that to the entire solar system and ask how long it would take to use up all the resources of the main belt asteroids and turn them into O'Neill cylinders, for example. And that answer is a few hundred years, which we also published. So there you go, I've finished. Thank you. And yeah.
Wonderful. Thank you so much. And again, we have time for a few questions before I ask you for your challenge. Danielle.
Does it really have to be just 20-meter towers? Can it be like 200-meter towers?
It can be 2-kilometer towers.
Yeah.
We've looked at that, yes, and I believe you can build them out of regolith. If you can sinter it into concrete, there's no, because of the low gravity, it's actually not quite feasible. Above about 1 kilometer, though, the mass in that becomes really huge. Yeah. So I think you can go up to 1 kilometer, and we've got the numbers for that too.
Thank you.
I'll be loud.
Please.
Oh, okay, no, I won't. So, you've concentrated on like the high value resources, yes. But then there's this concept that mass is a resource, just raw mass, or that a hollow stony asteroid could be turned into a habitat. Do you discuss that in your book?
Radiation shielding, it would be very useful.
Do you discuss those sort of bulkier, less concentrated value?
So the problem, I think, becomes, so first of all, yes, using asteroids as radiation shielding and turning them into vehicles. There's a list of the ones you could turn into Mars cyclers, and there's already a half dozen or a dozen that we could actually divert into those orbits now if we could learn how to turn them into habitats. So that's quite interesting as a bulk use. But the big problem with bulk materials is moving them around the solar system, because that's very expensive in delta V. So we don't really have the rockets for it. It would have to be slow, or you could use some low delta V transfer orbits that are not the usual ones, but they take longer. So it became tricky on a business case point of view.
Unless you use their mass themselves.
Well, then you have to want to be there. And whatever that random orbit is. Yes, yes, how do we govern the moon?
Oh, wonderful. I think you're not the only one who wants to discuss this. Wonderful. Thank you so much. This was great.